How physics explains the mystery of flight. A deep dive into travel. Flight represents one of humanity's most remarkable achievements, yet it is fundamentally grounded in well-understood physics principles. The seeming mystery of how aircraft and birds remain aloft dissolves when examined through the lens of aerodynamic forces, Newton's laws, and fluid dynamics. Understanding flight requires knowledge of the four fundamental forces at work, the principles that govern lift generation, and the sophisticated interplay between design and aerodynamic efficiency. The four fundamental forces of flight. All aircraft, whether commercial jets, gliders, or birds, operate under the influence of four primary forces. These forces must be carefully balanced to achieve controlled, sustained flight. Lift is the aerodynamic force that acts perpendicular to the direction of motion, counteracting gravity and allowing flight to occur. Without lift, no aircraft could remain aloft. Weight is the gravitational force pulling the aircraft toward Earth, determined by the aircraft's mass and payload, including fuel, passengers, and cargo. Thrust is the forward force produced by an aircraft's engines, whether propellers or jets, which must overcome drag to maintain or increase speed. Drag is the resistive force acting opposite to the direction of travel, caused by friction and pressure differences as the aircraft moves through the air. For sustained level flight, lift must equal weight and thrust must equal drag. The generation of lift. Multiple complementary explanations. The question of how wings generate lift has been the subject of considerable scientific discussion. The answer is not singular, but rather involves two complementary physical principles that together provide a complete explanation: Newton's third law and momentum change. The most fundamental explanation involves Newton's third law of motion. For every action, there is an equal and opposite reaction. Wings are specifically designed to redirect air downward through their shape and orientation. When a wing deflects air downward, the action, the air exerts an equal and opposite upward force on the wing, the reaction. This principle explains lift comprehensively and applies to all wing configurations, including symmetrical wings and even flat plates at high angles of attack. The amount of lift produced depends on how much air the wing diverts and how quickly it diverts that air. This can be expressed through momentum principles. A wing either diverts more air at a given velocity or increases the vertical velocity of the air deflection, or combines both approaches. Large aircraft with long, narrow wings can move more air slowly, while smaller aircraft must move less air more quickly to generate equivalent lift. Bernoulli's principle and pressure differences. Bernoulli's principle states that faster-moving fluids exert lower pressure than slower-moving fluids. When an aircraft moves forward, the shape of its wing causes air above the wing to move more quickly than air below it. This velocity difference creates a pressure gradient. The lower pressure above the wing and higher pressure below create an upward force, pushing the wing aloft. However, Bernoulli's principle alone cannot fully explain all flight phenomena. It struggles to explain how symmetrical airfoils or flat plates can generate lift at high angles of attack, where there is no upper surface curvature to accelerate the air. This is why aerodynamicists now recognize that an accurate, complete explanation of lift requires both Newton's third law and Bernoulli's principle working together. Wing design, the critical role of geometry. Aircraft engineers manipulate wing geometry to optimize aerodynamic efficiency, balancing multiple requirements to achieve the desired performance characteristics. Aspect, ratio, and induced drag. The aspect ratio of a wing, defined as the square of the wingspan divided by the wing area, profoundly affects aerodynamic efficiency. Wings with higher aspect ratios are longer and narrower relative to their area, and they produce significantly less induced drag. Typical aspect ratios range from 5 to 10 for small general aviation aircraft, 9 to 15 for commercial transports, and 30 or higher for sailplanes. The physics behind this relationship is elegant. A large wingspan affects a large cylinder of air, allowing the air to be deflected downward gradually. A small wingspan must deflect a smaller cylinder of air more sharply, requiring greater velocity changes and thus more energy, which manifests as induced drag. This is why fuel-efficient aircraft and sailplanes favor high aspect ratio wings, winglets, and effective aspect ratio. Winglets are small upright extensions added to wingtip regions to increase the effective aspect ratio without substantially increasing the wingspan. These devices redirect wingtip vortices, regions of swirling air that form at the wingtips, and effectively increase the wing's performance characteristics. Modern winglet designs, such as those on the Boeing 737 MAX, can reduce total aircraft drag by 5% or more, generating enormous fuel savings over an aircraft's operational life. Angle of attack and the critical stall angle. The angle of attack, AOA, the angle between the wing's chord line and the oncoming airflow, is critical to lift generation. As AOA increases from small values, lift increases steadily. However, this relationship is not linear. Beyond a certain critical angle of attack, typically 15 degrees to 18 degrees for most airfoils, the smooth airflow over the wing's upper surface separates, creating turbulence. At this critical point called the stall, lift suddenly decreases rather than continuing to increase. A stall is fundamentally a condition of airflow separation, not insufficient airspeed, a critical distinction for aviation safety. Once stalled, an aircraft rapidly loses altitude unless the pilot reduces the angle of attack to restore smooth airflow. Crucially, the critical angle of attack remains constant for a given wing design regardless of weight, altitude, or temperature. The lift-to-drag ratio and aerodynamic efficiency. Both lift and drag depend on similar aerodynamic factors: air density, velocity squared, wing area, and dimensionless coefficients. This similarity is captured in the lift-to-drag ratio, LD ratio, which measures aerodynamic efficiency. LD CL CED. An aircraft with a high LD ratio produces substantial lift while maintaining low drag. Under cruise conditions, when lift equals weight and thrust equals drag, a high LD ratio translates to lower thrust requirements and thus lower fuel consumption. For commercial airliners, this efficiency advantage compounds over thousands of flight hours, potentially saving tens of millions of dollars in fuel costs per aircraft over its operational lifetime. Center of gravity and aircraft stability. The center of gravity, CG, the theoretical point at which all an aircraft's weight is concentrated, profoundly affects aircraft stability and control. All aircraft must maintain their center of gravity within manufacturer-specified limits to ensure safe, predictable flight characteristics. Longitudinal balance, determined by the CG position along the aircraft's lengthwise axis, is the primary concern. If the CG shifts too far forward, the aircraft becomes difficult to control. If it shifts too far aft, the aircraft becomes unstable and potentially uncontrollable. The CG changes throughout flight as fuel is burned and cargo or passengers shift position. Pilots and flight crews perform detailed weight and balance calculations before each flight to ensure the aircraft remains within safe parameters. Control surfaces and aircraft maneuverability. Pilots control aircraft through three primary aerodynamic control surfaces, each affecting rotation about a different axis. Ailerons, located on the trailing edge of wings, control roll rotation about the longitudinal axis by deflecting in opposite directions on each wing. Elevators on the horizontal tail stabilizer control pitch, nose up or nose down rotation about the lateral axis by deflecting together. Rudders on the vertical tail fin control yaw, left-right rotation about the vertical axis by deflecting left or right. Together, these surfaces allow pilots to maneuver aircraft through three-dimensional space with precision. Propulsion systems and thrust generation. All aircraft except gliders require thrust to overcome drag and accelerate. Different aircraft types employ different propulsion strategies based on their mission requirements. Turbofan engines, dominant in modern commercial aviation, use large front-mounted fans to accelerate a large mass of air at relatively low velocities. This approach is more efficient than older turbojets, which accelerates smaller amounts of air to higher velocities. Modern turbofan engines have bypass ratios of 8 to 11, meaning 8 to 11 units of air pass through the bypass stream for every unit passing through the engine core. This high bypass ratio reduces fuel consumption while maintaining sufficient thrust for long-range flight. Propeller-driven engines operate on similar principles, using rotating blades to accelerate air backward, producing forward thrust as a reaction force. Jet engines continuously accelerate air through the engine, expelling it at high velocity and producing thrust equal to the rate of momentum change of the expelled air. Flight in nature. Bird flight. The fundamental principles of flight apply equally to birds, though they achieve lift and thrust through biological mechanisms rather than engineered structures. Birds employ three primary types of flight. Flapping flight involves continuous wing movement, with wings developing lift while being rotated forward by flight muscles to produce thrust. Gliding flight occurs when upward aerodynamic force equals weight with no powered propulsion. Birds maintain altitude by riding thermal updrafts or descending gradually. Bounding flight, used by smaller birds, alternates flapping bursts with folded wing ballistic phases, reducing energetic costs by decreasing drag during the ballistic phases. Hummingbirds represent an extreme specialization for hovering, beating their wings 43 to 80 times per second and producing lift on both the upstroke and downstroke through a symmetrical figure-8 motion. Most other birds employ simpler flapping patterns and rely on thermal soaring for long-distance, energy-efficient travel. The physics of stability and performance. Aircraft stability depends on the balance between forces and moments, rotational effects. For level flight, the aircraft must balance not only forces, lift equaling weight, thrust equaling drag, but also rotational moments about the center of gravity. The design of wings, tail surfaces, and fuselage must work together to provide inherent stability while remaining responsive to pilot control inputs. Performance characteristics depend critically on the relationship between wing area, aspect ratio, and aircraft weight. Heavier aircraft require larger wings or higher speeds to generate sufficient lift. Commercial transport aircraft sacrifice maneuverability for efficiency through large wing areas and high aspect ratios. Fighter aircraft prioritize acceleration and turning performance through smaller wing areas and lower aspect ratios, accepting higher fuel consumption. Flight, far from being mysterious, emerges as a direct consequence of fundamental physical laws. The four forces of lift, weight, thrust, and drag must be carefully balanced. Wings generate lift through two complementary mechanisms: momentum change of deflected air, Newton's third law, and pressure differences, Bernoulli's principle. Aircraft design optimizes aerodynamic efficiency through high aspect ratio wings, winglets, and proper center of gravity management. Control surfaces allow three-dimensional maneuvering. Propulsion systems overcome drag while generating the thrust necessary for acceleration and sustained flight. Whether the vehicle is a massive commercial airliner, a small general aviation aircraft, a sleek sailplane, or a living bird, the same physics governs their flight. Engineering genius lies not in defying these principles, but in optimizing designs within them, creating machines and structures that exploit aerodynamic forces with remarkable efficiency to achieve the human dream of flight.